let's look. Einstein's theory of relativity kind of comes along in what we call the mass-energy equivalence. Okay? And so this is when we look at energy, we look at the change in mass multiplied by the change in speed, or multiplied by speed. So when we're looking at this is the famous Einstein equation, E equals mc squared. We never say delta E is equal to delta mc squared. That's the official formula. But the change in energy, so kinetic energy final minus kinetic energy initial, potential energy final minus potential energy initial. Okay? Change in mass from final to initial. Where the contradiction comes into play is that when we're in physics 20 and we're learning the difference between mass and weight, your mass is your mass no matter where you are, right? If you weigh 170 pounds if your mass is 170 pounds on Earth, your mass will be 170 pounds on the moon, will be 170 pounds on Jupiter. Your weight will be affected by the gravity on those other planets or the other moons. But your mass, we always say your mass is your mass. Well, here now we're telling you that there's a change in mass. And you're like, what? So this is what it looks like. When we're looking at a neutron at rest, so keyword here, at rest, that means kinetic energy is 0. Okay, we're not in motion. So we're looking at energy. It talks about a neutron. What do we know about the mass of a neutron? This goes back to our first couple pages of notes. Is it on your data sheet?
Yes.
Okay. So what is the mass of a neutron? Okay. What's the mass of a proton? Double check on your data sheet. Funny that, hey? Where do we find protons and neutrons? In the nucleus, and we've always said that they were equivalent. Okay? So we look at the change in energy is equal to the change in mass times the speed of light squared. We know what the speed of light is. It's a standard, 3 times 10 to the 8. So 1.67 times 10 to the negative 27 kilograms. What's the change in mass? It's just the neutron, so there is no initial mass. And the speed of light is 3.0 times 10 to the 8 squared. Zero, because we didn't change it. It's just a neutron. It's not going from thallium to bismuth, or you know how we do a nuclear reaction and we go, if it's a beta decay and we go down, or if it's a beta positive we go up, or alpha we go down by 2. Okay, we physically change from one element to another element. You're going to have a change in mass, right? But right now we're just looking at a neutron, so it's just a neutron. We're not looking at the initial piece. No, so we're our final is a neutron and our initial would be nothing. That's just what this the 0 is confusing when there's nothing changing, but it's 1.67. You could just write 1.67 times 10 to the negative 27. You wouldn't have to put in the minus 0. Okay? So we get 1.503 times 10 to the negative 10 joules. Okay? Energy is measured in joules. What's the other unit energy can be measured in? Electron volts. Okay? In this particular case, because we have meters per second and we have kilograms, if we look, kilograms, meters squared per second squared. That is a joule. When we go back to sig digs, we see that in our mass constant we have 3 significant digits, which is the only number that we're dealing with. 1.50 times 10 to the negative 10. We are dealing with the speed of light as well. Okay. So this piece here, all of this to say something that I've already just said, is that mass equivalence helps explain why nuclear reactions, being fission or fusion, release so much more energy than a chemical reaction. So if, for example, we're looking at helium-4 and we react it with nitrogen-14, we see that we get oxygen-17 and hydrogen-1. And so when we use standard nuclear notation, which is what this piece here is, A over Z for X, the units for atomic mass are atomic mass units, which is what Daniel saw yesterday. So this U here, not to be confused with mu, but this is also mu, is atomic mass units. You can also see that, AMUs, for atomic mass units. Okay? So one atomic mass unit is 1.66 times 10 to the negative 27. Can you find this on your data sheet? We already say one elementary charge is 1.9, 1.6 times 10 to the negative 19. Can you find where one atomic mass unit is equal to 1.66 times 10 to the negative 27? Found it? On the left-hand side? All right. When you're using atomic mass numbers in conservation of nucleons, these values are rounded to the nearest whole number. Okay? On a smaller and more accurate scale, the total mass of all reactants is greater than the total mass of all products. So, kilograms of reactants is greater than the mass of all products. So the difference in mass known as mass defect. So there's your change in mass. Change in mass. And it's the missing mass, the one that's converted into energy. So when we go from the thallium to the bromine, and energy is released, that change in that mass is energy. Okay? Let's look at this. So this is where you really need to remember your different kinds of decays. So it says radium-226 will undergo alpha decay. So alpha has what symbol? The fish. Yeah, the Catholic fish. Okay? So what is the symbol for radium? You need to have your periodic table out. The three of you that weren't here, there's right here. That Rn or Ra, they're two different things. One's radon and one's radium and one's radon. We're looking for radium-226. It's going to be a transitional element.
Oh, yeah, found it. Radium-226,
Ra.
Like the Greek god. No?
Okay.
Egyptian god.
Okay, so now that you found radium, what is the atomic number for radium?
Number is 88.
88, right? Because the atomic number is Z. It goes at the bottom. All right. It undergoes alpha decay. So I'm going to get an alpha particle, which we know has 4 for an A and 2 for a Z. Okay. So what plus 4 will give me 226? 222. Well, 226 minus 4. Yeah. Okay. 2 plus what will give me 88? 86. So what is element number 86? Radon. Rn. Okay. So this is your nuclear reaction. You have to start here. And we can see that we're physically going from one element to a completely different element. Okay? So the atomic masses are 226.025410 atomic units for radium 226 and 222.017578 atomic units for radon and 4.002603 units for an alpha particle. It says calculate the mass defect. So it's asking us to find the change in mass. That's what mass defect means. So we know that change in mass is going to be the mass of the products minus the mass of the reactants. And we're going to look at the absolute value. We don't care if it's positive or negative. Okay? So, what are my products? My products are radon, which says that it's 222.017578 plus the alpha particle, which is 4.002603. And we're going to subtract the reactants, which is radium. Okay? And for that, we get what value? Okay, so we get the negative sign, but we put the absolute brackets around it, so it doesn't matter the sign. Okay, we just need the absolute value. These are in atomic units, but we need the mass to be in kilograms. So when we look at it, it's 1.66 times 10 to the negative 27 kilograms for 1 unit, 1 atomic unit. So then I get what for a value? Pretty small, almost as small as an electron, but not quite, a little bit bigger. Okay, so the specific answer for this question is calculate the mass defect. And so the mass defect, we still have to follow sig digs. We're just going to go with 3. That's pretty standard. Right? We have 9.11, 1.65, 1.67, or 6.65, sorry. So we did 3 sig digs is good. Next it says, one thing I wanted to kind of, let's just revamp this formula a little bit so it's a little more clear. In this delta M, let's go the sum of the mass of the products minus the sum of the mass of the reactants. Okay, the absolute value of, because then you'll know to take both of these components and add them together if we put the sum of, which is what we did here. This is the sum of, this whole piece here is the sum of the mass of the products, and this whole piece here is the sum of the mass of the reactants. Just so that the understanding is completely there. Okay, calculate the energy released by this nuclear reaction. When we're talking about nuclear physics, E is equal to mc squared. We've already figured out the delta M. So delta E, no, go back to the original. And we get what for a value? 7.812 times 10 to the negative 19? No, 13 joules, which would be 7.881 times 10 to the negative 13 joules. Now we can leave our answer here. It didn't tell us to specify a unit, but if it did specify electron volts, how would I get there? Yeah, you would do your 1 over half. I want electron volts, and I have joules. So it's 1.6 times 10 to the negative 19 in case you can't read or see that small piece. So 7.8121216 times 10 to the negative 13 divided by 1.6 times 10 to the negative 19 gives me what value? Yep, 4.88 times 10 to the 6 electron volts. And then, if we really wanted to be fancy, we could go one step more and we could put it in 4.88 mega electron volts, because there's times 10 to the 6 electron volts in 1 mega electron volt. It doesn't matter. I'm just showing you 3 different answers for the exact same answer. I would be perfectly happy if you stopped at joules. The more calculations you do, the more chances there are for error. Okay? So if they don't specify, don't go out of your way. Okay. It says calculate the energy released per nucleon for this nuclear reaction. Okay, so when we look at this back here, that information, this per nucleon right here, comes from this information right here. There are 226 nucleons in this. So per, I'm going to do this 2 ways. 7.81 times 10 to the negative 13 joules divided by 226, or either or. What do we get for an answer on either one? Okay, so either or answer, because they didn't specify. Okay, now we get into the violent part of atomic physics. Particle-antiparticle annihilation. Just what everybody wants to hear. So when two particles collide, we have the complete destruction of each of those particles, and we transform all of that mass into energy. And so antiparticle has the same characteristics and physical properties as the particle, only one physical property is opposite. Do you remember what it is? Your neutron and your antineutron. Okay. Omega. All right. This one says, calculate the energy that is produced when an electron-positron pair, so that was said first, exactly, neutrino, antineutrino, annihilate. That means when we see this word, all mass energy, all mass is converted to energy. Okay? And that's simply this formula. When I look at delta M, mass final minus mass initial or mass product. Let's use those. Let's not use mass initial and mass final. Mass product, mass reactants. Do we have any products? No. It's all completely converted. So this is 0. There is no final mass. What are the two reactants that we have? An electron and a positron. So we have 9.11 times 10 to the negative 31, because remember this is the sum of, so 9.11 times 10 to the negative 31 kilograms, plus what's the mass of a positron? Right, because a positron is just a negative electron. This can be written the same way as going 2 times 9.11 times 10 to the negative 31 kilograms. That says the same thing. What do we get for a value of this? Okay, so now I have my change in mass. Delta E, you've got lost. So all we're doing is in this question, there's no information given to us, like no numbers given to us. So when we set this up, we know what C is, 3 times 10 to the power of 8. What is the change in mass? When I look at change in mass, we know that it's the sum of the mass of the products minus the sum of the mass of the reactants. That's what we know that formula to be. When I look at the question, it says calculate the energy that is produced when an electron-positron pair annihilate. Annihilate means that there is no products. Everything went completely to energy. Okay? So there's no products. So then, what is the sum of the products? Well, there's an electron, or a reactant, sorry, and there's a positron. Those are the reactants. So then I have 0 minus. This is the same as saying 2 times 9.11 times 10 to the negative 31. And so 9.11 times 10 to the negative 31 plus 9.11 times 10 to the negative 31 is 1.822 times 10 to the negative 30. But we also look at the absolute value. So it doesn't matter that this is negative. 1.822 times 10 to the negative 30 kilograms is our delta M. Is that
I just got lost in like
this piece here?
so that is
Yeah. Are you good now for that piece, Kyle? We're not going to worry about sig digs because we're not at our answer. Okay, our answer is calculate the energy. So we're going to keep all decimals, and we're going to go over here into energy is equal to change in M times C squared. We know that the change in M is 1.822 times 10 to the negative 30. Speed of light, 3.0 times 10 to the power of 8 squared. And we get okay, and it doesn't ask us for electron volts. Why go that far, right? It's perfectly happy and perfectly legitimate to be 1.64 times 10 to the negative 13 joules. You could go to electron volts because times 10 to the negative 13 is a small number. That's up to you. The question didn't ask us to do that. Okay?